Okay, today I'll cover emerging technologies and hybrid memories, and I've added some slides on flash memory at the end as well, because that's an exciting area too. Error correction in flash memory, especially. And we're here, emerging memory technologies and hybrid memories. Maybe we can start quality of service if everybody's happy with it, or we can, because I don't have a whole lot of slides on emerging technologies. Because I wasn't able to prepare some of the very recent work that we're going to present at ISCA also. But I'll send out the paper. We're preparing the final version, which is due tonight. Okay. Yeah, that's this paper. Basically a case for efficient hardware-software cooperative management of storage and memory. And the idea over there is if we can unify with the emerging non-volatile memory technologies, if we can unify the management of storage and memory together, we can get rid of a lot of the overhead of system software in managing storage. Today, you access memory with loads and stores, but you access storage, disks or flash, with operating system level interfaces, right? You do file open, file close, file write, file read. These are very different from loads and stores. You can map that to memory, but that takes a lot of overhead to do memory mapping. So the idea here is if you have non-volatile memory that's very similar to DRAM in terms of latency, which we will talk about, which has very high capacity, then you can build a system that is a hybrid of many different memory technologies, and that provides the illusion of a single interface. So previously what we have is DRAM and flash and disk. So you have two interfaces, right? You have load, store here, and you have some operating system level interface where you do file read, file write, etc. Now, if your DRAM is here and you have something that's very close here, non-volatile memory, like phase change memory, now you can look at this as a unified hierarchy because the latencies are much closer to each other. And you have non-volatility here, which is very important. And maybe you have a single interface here, which we call the persistent memory manager, which also manages non-volatile memory also. But basically you have a single interface, load, store, and some hints from the application. And maybe you change the interface a little bit, saying what should be persistent and what should not be persistent. That's potentially a file. Now the persistent memory manager decides where the data should go and how it should be moved to maximize efficiency. This way the programming can be easier also because you get rid of a lot of the overhead of going through the operating system. And the idea here is this is not an operating system, this is more of a hardware accelerated manager. Very low level system software as well as hardware support. For example, you have hardware support for protection. Like file system protection is done in operating system today, but we're going to have hardware support for protection of files in the entire system here. So that's the idea. I'll send out the paper after we're done with the final version, but I won't be able to talk about it because they're not ready yet. But that's the idea. That's one of the interesting things these emerging technologies enable because they're non-volatile and they're very close to DRAM in terms of latency. Now we can think about having a single interface to the entire memory plus storage and manage the data much more efficiently. And our initial results show that you can actually, by getting rid of this system software management overhead of file system, you can improve energy efficiency. This is a workshop on energy efficient design. That's WEED. You can improve energy efficiency of the memory system by almost 10x actually. You can get significant performance improvement. It depends on the application, but you can get significant performance, significant energy improvements. Okay, I will not talk about that. Okay, this is what we'll cover, I think, Monday. And actually, we'll have a lot of material on Monday because this is an area we've been working on for a long time, memory quality of service. I can go on for days on that topic, probably. And I'll cover, actually, one of these works over here, too, because it's related to here as well. Whenever you have some flash memory, you need to manage errors. And I think increasingly a lot of other technologies will need to manage errors in a similar way. So we'll talk about this particular work over here. Okay, let's get started on the main material. I guess I've already covered this, so I'll go through this very, very quickly. Basically, the problem was main memory capacity and bandwidth need was increasing, and DRAM technology scaling is ending. And we also want main memory to be very energy and power efficient. And you've seen that this slide, which shows that memory capacity per core is expected to drop 30% every 2 years. And if DRAM scaling is also ending at the same time, we need to find a way of getting very high capacity memory to sustain what we need with multi-core. So I'm going to skip these. And we know the DRAM scaling problem from last time. Basically, there are several problems with DRAM as main memory that led us to consider some of these other technologies as part of main memory. The first is this: DRAM capacity is hard to scale going forward because of DRAM scaling issues, right? The second is energy and power is a key system design concern, and DRAM consumes high power due to leakage and refresh. And you've seen this in the last lecture, and we've devised methods to reduce this. And this is also true. So what do we want from an ideal memory system, and what can non-volatile memory actually provide? We remember this slide, right? Traditionally, we want enough capacity, low cost, and high system performance. And we want even higher capacity today, and we want continuous low cost, and we want higher bandwidth and low latency in high system performance. And we have these new requirements also. We want the technology to be scalable, going down to maybe 2 nanometers, or whatever is the lowest you can get, and energy efficient, and this is an orthogonal issue. So emerging resistive memory technologies can help these parts, I think. Higher capacity because they're more scalable, continuous low cost because you can reduce the size of them significantly, hopefully going into the future. And this is by definition, I think, technology scalability enables these things. And they're more energy and power efficient because they're non-volatile. Although we'll see that they're not very energy and power efficient if you're actually writing to them and reading from them. So we'll try to avoid that as much as possible. And that's where the caching policies come in. So the emerging technologies provide an opportunity, basically. We'll need to likely replace and augment DRAM with a technology that is scalable and at least similarly efficient, high performance, and fault tolerant, or can be architected to be so. None of these technologies are actually similarly efficient, high performance, or fault tolerant, but maybe we can architect them, change them, enable the system in such a way that they look like it. Some emerging resistive memory technologies appear promising, and I'll talk about mainly phase change memory here. And next week, Moin will hopefully talk about that also. He's done a lot of work, and Moin Dinkraishi from Georgia Tech, he's done a lot of work in this area also. So you can ask him, you can ask him the harder questions. And spin torque transfer, spin transfer torque magnetic memory is also interesting. And memristor is another option. And maybe there are other ones also. Actually, there are other ones, but they don't seem to be there yet. These are very interesting because these seem to be close enough in terms of manufacturability. The key question is, can we enable these technologies to replace, augment, or maybe even surpass, do better than DRAM? I think surpass would be a very tough thing to do given the characteristics of these technologies. So a little bit of background first. I think the key distinction between DRAM and flash and other technologies is DRAM and flash are charge-based memories. Basically, you write data to some cell by capturing some charge. In DRAM, it's the capacitor. In flash, it's something called the floating gate. Right? And you read data by detecting the voltage of that charge. Right? Or you could actually detect the current also. Right? Because this is charge-based, it's fundamentally not scalable, as we will see, because this charge is very difficult to place and control. On the other hand, resistive memories, like phase change memory, spin transfer, torque MRAM, and memristors, you write data by pulsing current. You inject current. And that's how long you inject that current and with how much current you inject determines what state you place the memory in. And then you read data by detecting the resistance. And you asked questions about the selector device. Moin may know more about that, actually. He's worked at IBM, where they've developed these selector devices. And I can actually point you to a paper related to that I looked up yesterday. That talks a lot about these selector devices. And it's not clear which one's the best one, by the way. it's always the case with these emerging technologies. But basically, they operate by detecting resistance somehow. You can actually detect the resistance with these selector devices that they have developed. And apparently, there's a lot of progress in this technology area. OK, so what are the limits of charge-based memories? What is the fundamental difference? If you look at a charge-based memory, it's difficult to place this charge and control this charge, especially as you scale the technology down to smaller sizes. So this is what a flash gate looks like. You have this floating gate, and how many electrons are here determines the state of this floating gate. Basically, whether you store a 0 or 1 is determined by how many electrons you have here, which also determines the voltage level. Same as here, is the capacitor charged or discharged, determines 0 or 1. In flash, it's more interesting because you can actually have multiple levels. You can divide the threshold voltage into multiple windows, as we will see. And with one single gate over here, you can store multiple bits. It's called multi-level cell technology. It's very hard to do that in DRAM. It's easier to do discharged or charged, which is 1 bit. But regardless, as you reduce the size of the charge storage unit, reliable sensing becomes difficult. Because you can imagine, right? If you have only 1 electron here, as you reduce the size, how can you sense that electron exists or doesn't exist? That's the fundamental limit here. Whereas if you look at some emerging resistance technologies, they operate in different ways. For example, phase change memory, you inject the current to change the material phase. So it's really fundamentally not the level of charge you have, but what phase you're in. And that phase can be detected. The key is, as long as you can detect that phase really well, it's a binary decision, right? Or detect the resistance really well. So that's why the selector device is very, very important. What enables that? It's either it's that part of the so you have in any memory you have 2 things, right? One is I would call the storage unit and the sensing unit. Right? You need to have both to be operable well. Storage unit in DRAM is the capacitor, and sensing unit is the sense amplifier, right? And we know how to build sense amplifiers really well. In phase change memory, storage unit is basically phase change material. And sensing unit is that selector device that basically determines the resistance. And that needs to work well. I'm not going to talk about that. I'm going to assume that they exist. And they do exist according to people actually manufactured this, and HP claims that they manufactured this. So I think actually Samsung is using some of these phase change memory in their cell phones as part of flash replacement. And this is not clear where it's used right now, but we're going to get some prototypes of this soon. OK, but basically, all technologies have this, and the hope is that these storage units are more scalable here, and these sensing units exist. So phase change memory works by injecting current to change this phase of the storage unit, and the resistance is determined by that phase. With spin transfer torque MRAM, the way it works is basically, I'll talk about this very little later on. You have a magnet, and you change the polarity of the magnet, orientation of that magnet compared to a reference layer. And if it's one way, it stores 0. If it's the other way, it stores 1, basically. And you inject current to change that polarity, and the resistance is determined by the polarity. It's pretty interesting, actually. It's a magnetic memory. And this is more scalable as well. And memristors, I don't understand this as much as the other ones. This is resistive memory from HP labs. You may have read about this. But basically, you inject current to change the atomic structure of the material. And the resistance is determined by the distance of the atoms. So that's, you can probably guess I don't understand this as well, but that's okay. The fundamental thing is it's, and I'm not sure if I can point you to the right papers because I think HP tends to be secretive about this a lot. But basically, this, the high-level operation is very similar. It's resistive memory. You can detect the resistance. So I'm going to focus on phase change memory because we've looked at this a lot, and we're looking at SCT-MRAM as well, but I'm not going to focus on that. But I'll briefly talk about that later on. This I showed you yesterday. Basically, phase change material exists in two states. It could be chalcogenide glass, it could be something else. Amorphous and crystalline. Amorphous state has low optical reflexivity. In fact, this is used in optical media today. Some form of phase change material is used in the CDs that you have. Except it's much slower, right? CDs are much slower. And whenever you write to it, you can see that, you can see the tracks changing, right? When you write to a CD, the written portion is different. So that shows that it's in a different phase. So we want to use a similar material, not the exact same thing, for main memory. And basically, in CDs, you determine this, when you read the CD, the sensing unit is different, right? You actually determine how much reflection you have optically, and that's how you read the CD. Whereas we're going to look at the resistance of a similar material, right? So basically, amorphous state has low optical reflexivity, and you can either detect that and high electrical resistivity, or you can detect that. We're going to try to detect that. And crystalline state has high optical reflexivity and low electrical resistivity, so there's that distinction between these two states, very clear. And you can map these two states to 0 or 1 now. Now you can switch the PCM cell between these two states reliably and quickly. I guess I've shown you this before also. Basically, you can write to the cell by changing the phase via current injection, and how much current you inject and how long you inject that determines whether you set the cell or reset the cell. And I've shown you this before. You can study the papers that I've assigned. I think the CACM, communication of the ACM paper, is the shortest one, and it's at a high level enough that you can get the ideas quickly. On a read, we need to detect the phase via material resistance, basically, and that's where the selector device gets it. Okay, I think I'll go through this quickly. So what is the opportunity, given that we have this material that we can reliably switch between 0 or 1, and we can read the resistance, and it's non-volatile? What are the advantages? First of all, it scales better than DRAM and flash. People have actually manufactured it at 20 nanometer. And this is a very old data. This is 2008. I believe people have manufactured it at much lower nanometers now. It's expected to scale to 9 nanometers, and this, again, old expectation. It's gone down to, I think, maybe 5 nanometers or so today, maybe 3. Somebody said 3, but I didn't read the paper. The reason is it requires current pulses which scale linearly with feature size. That current pulse you inject scales linearly with feature size. It can be denser than DRAM because you can store multiple bits per cell due to the large resistance range. If you look at this resistance range, it's relatively large, 10 to the 3 to 10 to the 7. Right? You can chop up that resistance range. As long as you can control which resistance you set the material to, then you can detect multiple bits. Right? And people have prototyped 2 bits per cell in 2008. And the expectation, you can see that it's a little bit older slide. The expectation is that you can get 4 bits per cell. It's non-volatile. It's been shown to retain data for greater than 10 years at a high temperature. And there's no refresh needed, so it has low idle power. And these are very interesting advantages that could potentially enable something like this. So when we first started looking at this, when we saw that DRAM is not scaling that well, we wanted to look at this technology and analyze it. So what we did in this paper, this is the longer version of the communication of the ACM paper. We surveyed prototypes of the phase change memory technology from many device level and circuit level conferences that were published between 2003 and 2008. And we tried to derive its latency, bandwidth, energy characteristics for an average phase change memory for feature size of 90 nanometers, because nothing was at that point, well, from 2003 to 2008, you have a very wide range in terms of technology. So we wanted to have apples-to-apples comparison between DRAM and phase change memory. So we tried to derive that parameter. And it turns out this is a very difficult task to do. Whenever you're dealing with a new technology, everybody has a very different number, and there is no normalization. So you need to do a lot of work to figure out what this parameter should be. And this is the table from one of the, actually this is a better table from the ISCA paper. That basically looks at different parameters. This is the technology survey we did. And these are different papers that were published from different manufacturers as well. I believe these are all manufacturers, Micron, Samsung, and other manufacturers that looked at phase change memory. And you see that some of the data elements are missing even in this academic survey. For example, some people have not even specified the read time and read current. So we tried to do our best to come up with some parameters. But basically, these are the parameters we've used, and I'm going to show that next. Oh, over here. So at the high level, if you look at phase change memory, if you look at its latency properties, its latency is comparable to but slower than DRAM. This is a typical access latency in terms of processor cycles for a 4 gigahertz processor for different types of memories that we have today. L1 cache is approximately 1 to 5 cycles, right, in SRAM. Last level cache is embedded DRAM, let's say. It's maybe on the order of 20 to 100 cycles. DRAM is on the order of 500 cycles. And phase change memory is on the order of 2 times or 4 times DRAM. Depends on read or write, but it's somewhere around here. It's much closer to DRAM than it's to flash. Flash is on the order of 2 to the 17 cycles. And hard drive is almost inaccessible now, right? That's why when you put flash into your system, it speeds up significantly, right? And there used to be tape somewhere over here, but still people use it. It's part of the hierarchy, but it's not the general part of the hierarchy of the general public. So these are the parameters that we're going to assume, which are actually still similar, I think. Read latency is 4 times that of DRAM, and it's much faster than NAND flash, which is good because now this could potentially be used at main memory. Write latency, unfortunately, is much worse than DRAM and similar to flash. It's 12x DRAM. And this is going to be a problem in a lot of memory technologies, new memory technologies we're going to examine. Write bandwidth is 1/10 of DRAM and similar to flash again. Dynamic energy is another problem with this technology. For reads, it's 2 times DRAM. For writes, it's 43 times that of DRAM. It's similar to flash. So again, writes, you can see that it's a problem, right? Because you're injecting a lot of current. As a result, you're wasting a lot of energy with this technology. Endurance is an issue. This is not an issue with DRAM, right? Basically, when you write to a cell, a phase change happens at 650 degrees Celsius, which is very high, right? What happens is that contacts that enable the writing degrade from thermal expansion and contraction because of these high temperatures and high change in temperatures. As a result, you cannot sustain many writes. As you keep writing, those contacts degrade, and over time, you cannot write to the cell. So you get 10 to the 8, approximately 10 to the 8 writes per cell. And this is, of course, for DRAM, we never had this issue. For DRAM, it's so long, endurance is so long that this has never been an issue as far as we know so far. For flash, this has been an issue. For flash, this number is 10 to the 5 writes per cell. A cell in flash dies after 10 to the 5 writes. So that's why flash controllers do a lot of wear leveling. They try to ensure that whenever you write to a physical block, you don't write to it again. They remap the logical block to some other physical block if you keep writing. So they try to level how much writes each physical block receives. That's why you have this flash translation layer that sits in between. That's basically a processor that does management of flash memory. Because 10 to the 5 is a very small number, right? Here, 10 to the 8 is a much larger number. But if we're planning to use it for main memory receives a lot of writes, right? Because this is also a fast memory. So this is going to be a problem. How do we solve the endurance? How do we ensure that the main memory capacity doesn't degrade, right? And people have looked at this, and Moin will probably talk about that next week. Okay, the cell size is an advantage with phase change memory. Basically, if you use single level cells, you can have, this is the feature size, this is how you evaluate the cell size of main memory, 9 feature size square. Basically, it's the area of the feature size, right? And this is expected to scale well as you go down. Basically, this is, at this point, what we assumed was 1.5 times DRAM, which is bigger than DRAM cell, but and it's 2 times or 3 times bigger than the NAND flash cell, but it will scale with feature size as we go forward. And with MLC, multi-level cell. That's the hope. And it seems like it's going to happen. So if we would like to summarize, what are the pros and cons of this technology over DRAM? First, we get better technology scaling. Second, it's non-volatile. Third, we get low idle power because of no refresh. Cons are significant. You get higher latencies, 4 to 15x of DRAM, especially for writes. Higher active energy, 2 times to 50 times of DRAM, especially for writes. And a lower endurance, a problem that we didn't see before in DRAM. A cell dies after some number of writes. And people have been projecting that this number will increase to 10 to the 12, but we haven't seen that yet. There may be prototypes with 10 to the 9, but it's not clear how that will go. So obviously, because of these cons, there are challenges in enabling phase change memory as a DRAM replacement or helper technology. So in order to enable this, we'd like to mitigate the shortcomings, find the right way to place phase change memory into the system. It's not clear this place is the right place. For example, some other place could be using it as storage, right? And I think this will be done, and I don't think there are a lot of issues there. That's not an interesting research problem, in my opinion, at the architecture level. Maybe at the system level, it could be interesting because what do you do with very fast non-volatile storage over here? How do you partition your application such that you can take advantage of that is an interesting research issue. But how do you architect that is less interesting because it's another level in the storage hierarchy. But if you would like to use this as part of main memory, then how you architect that is a research issue because it's not clear where you place it, right? Do you replace DRAM? Do you have hybrid memory? How do you control it? What data do you place over here versus here in the architecture? It becomes a problem. And how do you ensure secure and fault-tolerant phase change memory operation given these challenges? Because lower endurance actually leads to security issues as well, right? You can have an application that keeps writing to memory and it destroys memory for all other applications if you have a multi-core system. So there are several research challenges. Where do you place the phase change memory in the memory hierarchy? You could have operating system controlled phase change memory and DRAM. You could have operating system controlled phase change memory and hardware controlled DRAM, right? Because now DRAM can become smaller and maybe you can have it as a cache. You could have pure phase change memory, main memory. You could get rid of all of the DRAM. And we're going to be aggressive and we're going to explore this option first.
But it seems impossible with the numbers that you give.
With the endurance issue?
You can also rewrite.
That's right. After some point, you get rid of your main memory.
As far as I see, PCM is used usually as a replacement of flash, usually.
Today, yes, that's right. Today, people have actually systems that use it as a replacement or helper for flash. Yes, yes. But we're going to try to be more aggressive. I think that a lot of interesting research issues come about once we're more aggressive. And we'll see that this doesn't work, actually. That's a good conclusion, but it's good to see the limits of when it doesn't work and how bad it is, at least in current state of the technology. OK, so the second question is, how do we mitigate the shortcomings of phase change memory? And we'll take a look at some approaches. And how do we minimize the amount of DRAM in the system? And we're going to look at this approach in particular. Phase change memory is the main memory, and DRAM is a cache for phase change memory. And how do we take advantage of byte addressable and fast non-volatile main memory? This is more of a system level issue also. If you have very fast non-volatile main memory that's addressable, you can actually read every byte out of it. Whereas flash is very hard to read every byte because it's block based. And we can get to that if we have time. And can we design techniques that are agnostic to the technology that we have? So right now we've been talking about phase change memory, but maybe some other technology will become successful, right? Can we design techniques, architectures that are agnostic to the particular characteristic of phase change memory or MRAM, for example. I think this is important, otherwise we'll develop too specific techniques. And I've seen that in the research community, which may be dangerous in the techniques you develop, right? And the technique will not work well for some other technology. Okay, so how should phase change memory-based main memory be organized? If you look at this, this is what we have today, and this is an abstraction. You have memory controller controlling a bunch of DRAM. Maybe in the short run, this is interesting. You replace some amount of DRAM with phase change memory, and you design the memory controller such that it is intelligent. We'll take a look at that. And this is actually what Moin had introduced in his ISCA paper. Hopefully he'll talk about that next week as hybrid memory. And other people have also looked at it, and we've been looking at it as well. Then the key question over here is, how do you partition and migrate data between phase change memory and DRAM? A more aggressive, well, I guess let's take a look at some system challenges when you have this hybrid sort of memory. Partitioning is a big challenge, I think. Should DRAM be a cache or main memory, or should it be configurable? And what fraction of entire system should be DRAM or main memory, especially given the endurance problem, right? How many controllers should you have? Who manages the data allocation and movement? And how do you do the data allocation and movement to minimize energy, maximize performance, maximize lifetime? I think these are very interesting optimization problems as well when you actually have this type of memory. What are good control algorithms? And how do we prevent degradation of service due to wear out? Because at some point this will wear out, or unless you're really lucky that everything is cached in DRAM, but that doesn't happen. Design of the cache hierarchy and memory controllers on the operating system is interesting too. How do we mitigate phase change memory shortcomings and exploit the advantages? And I'll talk a little bit about what we did, design of the phase change memory and DRAM chips and modules. If we can rethink the design of these new technologies with the new requirements, perhaps we can enable better chips than we were used to today, right? Because this is a new technology, and DRAM is an old technology that's harder to change, but with new technology, if we can incorporate some system level requirements into the chips, then we can get a much better technology than before. So a more aggressive alternative is probably replacing DRAM entirely with phase change memory, and this is what we had looked at when we started first. Basically, then the key question is, how do you actually tolerate all those shortcomings when you expose all of those shortcomings directly into the memory controller? Right? Any questions so far? So I'll introduce the STT-RAM technology also. This is also interesting, I think, and it's also always good to keep in mind how you can use this other technology as well. And I'll point you to this paper that talks about how you can design an energy-efficient main memory with STT-RAM, spin transfer torque. I'll just give you the basics of how this operates, because I think it's interesting. Basically, this operates using a material called magnetic tunnel junction, which consists of two magnetic layers. One is free, this is the free layer, and that's the reference layer. And you have some barrier between them. Free layer can be, its magnetic orientation can be parallel or anti-parallel to the reference layer. And that's what decides the difference between a logical 0 and logical 1. The cell looks very similar to every other memory cell, right? You take this magnetic tunnel junction, and you have an access transistor, and you have a word line. So it's similar to DRAM, right? It's similar to phase change memory also, except this material is different. So when to read this cell, we apply a small voltage across the bit line and the sense line and read the current out of this. To write to the cell, we push large current through this magnetic tunnel junction and change the orientation of the free layer. Make sense? And the direction of the current, which direction you apply the current, determines which direction you change this free layer. It could be this way, it could be this way. And it turns out if you apply the current not long enough, you change the free layer halfway, for example. And that doesn't work because that becomes unreliable. Now it doesn't retain the data. If you apply writes for a long enough time, then this becomes non-volatile. So there's an interesting trade-off. How long you apply the current and how much current you apply to change the direction determines how volatile the memory is. So this has this interesting trade-off that doesn't seem to exist in phase change memory. You can build different types of STT-MRAM, or actually get different types of volatility depending on how much current you apply. And that exposes new trade-offs, right? Which are not exploited as much. But also, if you don't apply long enough current, you can have unreliability as well, because you're more susceptible to errors if your free layer is not perfectly parallel or perfectly anti-parallel. Okay, what are the pros and cons, similarly to the analysis we did before of STT-MRAM compared to DRAM? Well, pros are very similar to phase-change memory, right? It's better technology scaling, non-volatility, low idle power. Cons, this doesn't seem to have an endurance problem, which is good. But it has higher write latency, higher write energy, and maybe reliability is an issue because it either takes a long time to change the orientation of the free layer, or it's not as reliable with the current manufacturing technologies. So this is not very clear. But the good news is this doesn't have the endurance problem. So some people initially have thought that this is one of the this is a better potential replacement for phase change for DRAM, and it could be. And people are actually considering this as a potential replacement on chip for caches. And you can probably find out the papers. And this does provide another level of freedom. You can trade off non-volatility for lower write latency and energy by reducing the size of the magnetic tunnel junction or by reducing the current. Okay. So this you can think about. I think this is an exciting research area also. Yes.
Write latency changes with respect to the current you apply.
That's right, yeah.
For DRAM, you do not need non-volatile, actually. It will be volatile, so you can keep it short.
That's right, exactly. You can keep it short. And you can keep the write latency actually very similar to even on chip caches with this, but then you'll get volatile caches.
Yeah, so this is what actually, this is not very important actually, you know.
That's right.
If you are making a fast change on data, that is, for example, you are just processing some data in a loop, then it will change very frequently.
Sure.
So it need not be non-volatile.
That's right, exactly. So you could take advantage of this level of freedom, I think, in different ways. But all of this depends on the reliable operation. So that's not perfectly clear yet. Okay, let's take a look at phase change memory. We'll focus on phase change memory for the rest of this lecture, because that's the technology I know most about. Basically, this is our initial study. I mentioned that we did a technology survey, and I gave you the parameters. I'll summarize them over here. Density, we're going to assume that it's higher than DRAM, but we're not going to use this in the results. We're going to assume that density doesn't matter, just to do an apples-to-apples comparison. Although I'll show some of Moin's work later on that shows that if you take advantage of this, you can get even more benefits in hybrid memories. Latency, we're going to assume 4 times read latency and 12 times write latency of DRAM. Endurance, we're going to assume a cell dies after so many writes, 10 to the 8 writes. And energy, we're going to assume 2 times read energy and 43 times write energy over DRAM. So this looks pretty bleak. But what will come to our rescue is caching. So there are 2 things that will come to our rescue. One is caching. So we're going to re-architect the phase change memory chips such that we have better caches inside them. And the second thing is low idle power. So there won't be any refresh energy that we're going to consume. So this is results without doing all of that. This is if you naively take DRAM and replace it with phase change memory with the parameters that I've discussed and organize phase change memory the same as DRAM. You have the same row buffers, same banks, same peripherals. You just change the, I guess, one transistor, one capacitor cell to phase change memory plus access transistor cell. And the results are pretty bad. You get, actually, it could be worse than this. I think these applications are not memory intensive enough. But you get 60% performance degradation, 120% increase in energy, and 500-hour average lifetime. So your memory dies after 500 hours. You don't want that, right? And there are some applications actually that die even less than 500 hours. And I don't know what that is. 0.01 years, for example, for this very memory intensive application. So this is probably not a good idea, right? But it's good to examine, right? There are some applications that can actually sustain 0.18 years. As long as you have very good caching, you don't access memory, right? Okay, so this is not going to work. So we've looked at how can you make it a little bit better. how can you actually re-architect the phase change memory to mitigate the shortcomings that we have. And the key realization is that DRAM, remember when we talked about DRAM, it needs to operate at this large row granularity, right? And whenever you need to read a row, well, it's organized with large rows so that you maximize space efficiency. But whenever you read a row, you destroy the cells, which means that you need to have a large sense amplifier buffer over here. Whereas in phase change memory, whenever you read a row, reads are not destructive, right? They're non-volatile. So you don't need to have a single sense amplifier that's wide. You can just read part of the row, and you can have many of these sense amplifiers that store different parts of the row. So that's the idea. You basically have small sense amplifiers and some latches that just buffer other rows, other parts of the rows. This way, you can have buffering of more than one row at the same area cost. And we've actually found that instead of having a 2 kilobyte buffer in phase change memory, having 4 512 byte buffers provides you much better caching opportunity. That's the idea. And the key realization is that reads are not destructive in DRAM, in phase change memory. That's why you can do this. So you can reorganize the phase change memory chips by taking advantage of this non-volatility of the chip. Now, this reduces array reads and writes because now you have a better organized cache. Right? If you're going through multiple rows, first of all, you don't access phase change memory. And you get better endurance when you're writing because you can write to this sense amplifiers and not into the phase change memory. And you get better latency and energy because you're not writing or reading from the array access. So the key thing is we would like to avoid this array access in phase change memory because that's what caused us a lot of problem. So we're going to organize the structure such that you can do better caching. The second thing is we write into the array at cache block or word granularity. In DRAM, in a sense, when you have sense amplifiers that are this wide, you basically write everything back into DRAM, right? Because reads are destructive, and you somehow have this feedback loop that writes everything back from the sense amplifiers, from the buffer, all the way into DRAM. Whereas in phase change memory, you don't need to write back things that are not modified, right? So basically, the idea is to keep track of what words or even what bits are modified here, and write into the array at that granularity. So if only one bit is modified, just write that bit. Of course, that has a lot of overhead, but people have proposed that idea also. But we've looked at it as a cache block or word granularity. And this basically having a dirty bit per word and writing only those words that are dirty gives you a lot of wear leveling benefits. Well, not wear leveling benefit, but reduces unnecessary wear so that you don't write unnecessarily. So if you do this, if you do these very simple optimizations, it turns out you can get much closer to DRAM. But I'll give you the caveats too. This is the same workloads. Basically, you get 20% performance degradation if you do these optimizations. You get on par energy, and you get approximately 5.6 year average lifetime. That's up from 500 hours. And the hope is that as you scale the technology, that would improve energy, endurance, and density. But there are several caveats, I think, that make this a not great alternative. One is worst case lifetime is much shorter, right? 5.6 years is average, and some applications that like caching benefit, but there are some applications that are much worse, right? Half a year or maybe a year over here. And you can actually write an attacker application that kills your memory much faster than that. And that's an interesting research area that people have explored over time. The second caveat is perhaps, well, intensive applications see large performance and energy hits. So if you look at this, some of the intensive applications, this one, the FFT computation, its performance reduces by 60% almost. And its energy increases significantly. And these are not the most intensive applications in the world. You can write, again, much more intensive applications that try to reduce performance and energy. Or reduce energy efficiency. And the third caveat in this study is perhaps we've used optimistic PCM parameters. I can never be sure. I can still not be sure what PCM parameter is optimistic or not optimistic. But that's usually the case whenever you're trying to deal with an emerging technology that doesn't really exist yet. Or that does exist, but that doesn't really exist in a form that's mass manufactured and that's targeted towards the thing you're trying to enable. But this is still important research to do going forward, I think, trying to enable emerging technologies. Otherwise, who will enable those emerging technologies, right? So, okay, so based on these caveats, maybe even architected phase change memory as main memory replacing DRAM fully is not a good idea. So we've been exploring hybrid memory systems as an alternative, and we'll take a look at that for the rest of the lecture. Any questions on this? Okay. I guess we don't need to take a break yet. But hybrid memory systems, I've shown you this picture before. If you have different technologies that have some shortcomings, maybe you put them together, right? And try to manage the data movements and allocations such that you get the best of multiple technologies. And we've seen, and the goal here is perhaps we should try to minimize the DRAM in the system because it's a very costly technology. And we should try to maximize the phase change memory in the system because it's non-volatile. Although that will cause us some problems later on also. And there are many questions, I think, in the design of such a system. And maybe, who knows, maybe STT-RAM also goes here, right? That's another possibility. How do you design the system? How many controllers you allocate? Who manages the data movement? They're all open research questions, I think. One option that we've been exploring and others have been exploring is using DRAM as a cache for phase change memory. So phase change memory is main memory. It's exposed to the software. DRAM caches memory rows or blocks. Now the benefits of this, you get reduced latency on DRAM cache hit, and DRAM cache filters a lot of the writes. If you have a large enough DRAM, let's say 1 gigabyte, it filters a lot of the writes before they go into phase change memory. You could even write everything to DRAM and bypass main memory and write things to flash so that you don't keep writing stuff into phase change memory, right? Or write things to disk directly. Basically, it can act as a large write buffer. And memory controller hardware manages this DRAM cache. That's our design choice because this eliminates system software overhead. If we used DRAM cache as main memory here, a small DRAM cache, and if we tried to move data between phase change memory and main memory, phase change memory and DRAM, every time we do that, we invoke system software. That would be a lot of overhead. That's what I discussed over here also. Similarly, you can think of DRAM and phase change memory here. And every time you do that movement, you invoke system software. That's a lot of overhead because the latencies are very low, right, between DRAM and phase change memory. There are 3 issues that I think should be tackled other than what we've discussed already. What data should be placed in DRAM versus kept in PCM? What is the granularity of data movement? Do you move the data as large pages now? Large pages are nice if you're moving data between disk and DRAM because there's a lot of latency, right? But large pages may not be a good option if the latency difference is very small, right? So we're going to look at that. How do you design a low-cost hardware-managed DRAM cache? This turns out to be a problem also because if DRAM cache is large, you need a large tag store also. How do you organize that tag store? How do you access the DRAM cache becomes an issue. And all of these topics, I think, Moin will talk about too. So, and it seems like we've converged in similar designs coming from different directions. So what he will talk about will probably enhance similar things. So there are 2 idea directions that I will explore. One is locality-aware data placement, which targets the issue of what data should be placed in DRAM versus kept in PCM. The second is how do you design a low-cost hardware-managed DRAM cache, cheap tag stores, how do you enable this, and dynamic granularity of data movement. I'll briefly give you the key ideas, high-level ideas. You can read the papers. But before that, I'll talk about what Moin did, just to give you a teaser so that you can attend this talk as well. But basically, he had a similar goal. He used DRAM as a cache for phase change memory. His goal was to achieve the best of both DRAM and phase change memory. And the idea was to minimize the amount of DRAM without sacrificing performance and endurance, and use DRAM as a cache to tolerate the phase change memory latency and write bandwidth. And the hope is that this phase change memory can be scalable to provide large capacity. So it will provide a capacity that's much larger than DRAM could provide at the same cost. And this is what the system, this is actually his slide, this is what the system looked like. Basically, you have this processor that accesses this DRAM cache, and you have some tag store which is a critical issue actually, how you design the stack store to be scalable. And you have a write queue, you had a write queue over here, and you have this phase change memory based main memory. So there were some write filtering techniques that he employed. Basically, pages from disk were installed only in DRAM first and not in phase change memory. So when you bring a page from disk, you bring it into the DRAM. That way you get rid of additional writes to phase change memory, right? You reduce the endurance, which makes sense. You could do partial writes. Only dirty lines from DRAM page are written back to phase change memory. Again, this is a very similar idea, right, to what we've described. We said only dirty words need to be written back. And page bypass. You can discard pages with poor reuse on DRAM eviction. So for example, when you have a page over here in DRAM that's not reused, that you predict that it's not going to be reused, you can just put it back to disk. That's what we've discussed also. So if you do this, you can actually get much better performance and endurance from phase change memory. And these are some of the results that they had. Basically, they simulated, here they have the benefits of a large phase change memory. So they actually simulate the page faults also. And this cannot be done with Symix, by the way. If you're wondering, this is impossible to do in Symix. So you cannot, it's very hard to get that result with a system level simulation. So you need some analytical model to actually get this result. So you can simulate a 16-core system with 8 GB DRAM main memory at 320 cycles. And the simulation hard disk latency is 2 milliseconds. And you have some flash latency, 32 microseconds, and flash hit rate 99%. So actually, it's interesting how to do the simulation. And you can ask him about that next, in the next lecture. The assumption is that phase change memory is 4 times denser and also 4 times smaller. It's again very similar to what we had, although we were less optimistic about the density of the phase change memory. 4 times is a little bit higher than what we had at the time. But the hope is that it'll scale. So the DRAM block size is similar to phase change memory page size. So if you look at this, these are some applications from databases and other workloads. This is normalized execution time, normalized to 8 GB DRAM. And this is 32 GB PCM, the blue bar. So if you look at this, the performance improves by 2x if going from 8 GB DRAM to 32 GB PCM. So this is different from our result, right? We never assumed any benefit from from increased capacity. If you take into account increased capacity, this is probably true. So you get a lot of benefit from increased capacity from phase change memory because the hope is that phase change memory is 4x denser. For a given cost, you can have much larger memory. Now this is true, I think. There are benefits to this, but if the application already fits in 8 GB, then you are losing performance, right? Then the additional capacity doesn't matter. So, and this is the performance with 32 GB DRAM. Obviously, it's much better than 32 GB phase change memory. And this is what happens if you have hybrid memory, 32 GB phase change memory plus 1 GB DRAM. So you lose a little bit compared to 32 GB DRAM, but you're still very good, right? So you kind of get the performance of 32 GB DRAM by having 32 GB PCM and 1 GB DRAM, assuming that you model the entire system, which is, I think, very promising.
What will happen if I have 33 GB DRAM?
Yeah, so you can ask him. I don't know the answer to that. my guess is it won't help as much. Maybe you'll go down a little bit more, slightly more, but not too much more. But that would be a good comparison point. I agree. Or maybe he has it in the paper and not in the presentation. Okay. So basically, the key conclusion is PCM DRAM hybrid performs similarly to similar sized DRAM. And also, you get significant power and energy savings. If you look at this, this is the power of 8 GB DRAM. And this is the power of the hybrid memory. And this is the power of 32 GB DRAM. 32 GB DRAM consumes much, much more power than a hybrid memory. And 33 will consume a little bit more. That's the trade-off, I think. And this is the energy. Again, hybrid memory is actually better. And this is the energy delay product. Hybrid memory is better. And his results show that average lifetime is about 9.7 years if you do this, taking into account the whole system. So there are no guarantees again. OK. So hopefully that gives you an idea of...
But since the size of the memory is bigger, obviously the lifetime is increased. Because
Oh, I see. Mm.
yes,
That's right, yeah, because we assume much smaller. Yeah, that's right.
it's much smaller, so.
That's right. And the hope is that, I mean, if it's a scalable technology, the size of the memory will be bigger, right?
Actually, what size, what was the size that you...
4 gigabytes.
4
Yeah, it was
gigabytes.
much
So 4
smaller.
5 years, 32 gigabytes.
Yeah, it doesn't scale, I think.
So
Maybe his applications were more intensive, though.
the size, he has just multiplied the size of the RAM by 4. However, lifetime increased by 2.
That's right. But I think his applications were much more memory intensive. Some of these applications are very memory intensive. These database applications and some breadth first search applications. Okay. Any other questions? How is the camera doing?
5 minutes.
5 minutes. Should we take a 5-minute break? This seems like a natural place, and then we'll continue.
And
Okay.
also we can just order some tea.
Okay, that sounds good.